Good afternoon, everyone. I hope you're all well. It's Dr. Bennett here, and today we're going to be starting chapter 9 from the textbook, which is all about friction. So, as always, we'll go over the theory first, and then at the end of this little tutorial, we'll have a look at some examples. So, first of all, let's define what we mean by friction in this case. Well, we're going to be just talking about what's called dry friction, right? So we're considering two dry surfaces rubbing together, as opposed to like lubricated surfaces, which then becomes like a hydrodynamics problem. And what we have is if two surfaces are in contact that have something called roughness associated with them, then friction arises between those interactions of those two surfaces, right? So the textbook shows this example of a book on a table, right? And if you zoom in to kind of microscopic level, each of those surfaces has a roughness associated with it if you zoom in, which is where the friction arises, because you've got these two rough surfaces trying to slide across each other, right? And the magnitude of the frictional force is proportional to how rough these two surfaces are, and also it's proportional to the weight of the object that's trying to slide across the surface. So that's what I've summarized here, and we'll formulate this into an equation in just a second. But basically, the force required to get an object to slip across the surface is proportional to the roughness, as we've just said, and also to the object's weight. And it should be fairly intuitive to you also that less force is required to keep an object moving across a surface than is required to start it moving in the first place, right? So if I've got this book and I'm trying to slide it across the table, it takes much more force to start it moving than it does to keep it moving, right? And the reason for that, as is well described by the textbook again, is that if we have a surface that's already started to move, then there's less points of contact between one surface and the other as it starts to slip across these sort of gullies and peaks, right? So because you've got less points of contact, there's less frictional force. So that's the reason why it's easier to keep an object moving than it is to start it in the first place, right? So that should be fairly intuitive. So let's go ahead and formulate that with an equation. So we have two different coefficients of friction. We have the one where it's in a stationary situation, called the static coefficient of friction, and then we have the one where it's moving, or it's already started to slide, right? And that's called the kinetic coefficient of friction. So let's deal with the static coefficient first. So this is basically the maximum frictional force between two surfaces in contact but are not yet in motion. And we say that the frictional force is equal to the static coefficient of friction, given the symbol mu subscript s for static, multiplied by the normal force, which, for my example that I'm going to describe in a second over here, is equal and opposite to the weight of the object. So just to put some numbers on this coefficient here, for example, if we have a metal on metal surface interaction, then we're looking at numbers around 0.15 to 0.2. But if we're dealing with like a racing car going around a corner, for example, then rubber on concrete or asphalt will be somewhere in the region of 0.5 to 0.9. So these coefficients of static friction will be between 0 and 1 based on how smooth the corresponding surfaces are. So in my example over here, I've just got a box on the floor, for example. I've drawn on the force vectors that are at play here. So let's assume that we've got some force applied parallel to the surface on the box. Then the frictional force, the frictional force that's associated with the static coefficient of friction is opposing the force that we're applying. So we're assuming that this box is still stationary, and therefore we formulate it with the static coefficient of friction. And then we say that the normal force that goes into this equation is equal and opposite to the weight of the object. So what this allows us to do is calculate the largest force, F, which can be applied without the box slipping. So we just have to solve this equation here for F, right? But then if F exceeds this frictional force, right? So this is just the right hand side of this, yeah, because F is equal to this if it's stationary, right, or in equilibrium. Then if F exceeds this frictional force, then the box starts to move, obviously. So that's the static coefficient of friction. The kinetic coefficient of friction is the one where the box has already started to slip, and we have less points of contact, and therefore the frictional force is less, right? Like the example that we just discussed. So in this case, we're expecting mu k. So mu, again, is the coefficient of friction, and k, subscript k, tells us that it's the kinetic one. We're expecting this value for the same two surfaces to be less than the static coefficient of friction, right? For the reasons that we just discussed about the points of contact. And the equation for that frictional force is exactly the same. So that's the theory. Let's go ahead and have a look at a couple of examples of that. Alright, so let's have a look at a couple of examples then. Let's have a look at one of each, as in one of an example of a static coefficient of friction question, and then example 2 that I have will be of a kinetic coefficient of friction example. So in this first example here, I have a 5 kilogram block or box sitting on an incline of 30 degrees. Flashbacks to mechanics from high school, I guess, right now. I have a static coefficient of friction of 0.2, and the question is to find the range of horizontal force F where the block remains stationary. So the key here is this word range, right? So we need to work out what's the smallest and what's the largest F such that this box stays in the same place. So there are two scenarios there, right? The first one is that when the force is large enough so that the box is almost about to start moving up the slope. So that's the first scenario. The second scenario is that the force is almost becoming too small in that the box is going to start to slide down the slope, right? So that's what I've summarized here in blue. So the first case is where the box is about to move up the slope, so F is becoming large enough so that it's going to start to push the box up the slope, and in that case the friction is acting back down the slope, right, because it's opposing F, or opposing the direction that it's about to start to move. In the second case, where F is small so that the box may start to slide back down the slope, then the friction acts in the opposite direction because it's opposing the motion that's about to start to happen. So we have to formulate this problem with these two different scenarios in mind to come up with basically two values of F, one small and one large. So that gives us the range of horizontal forces which keeps the box in the same position. So let's have a look at both of those two situations. So, by the way, I'm on the Mountain Dew today because I felt a little bit E-number deficient. so yeah, Mountain Dew today instead of Gatorade. So the first scenario here is what I've sketched out. So we said when the box is at the instant where it's just about to start to slide up the slope, then friction acts back down the slope, opposing that motion, right? And we're told that the frictional force is 0.2, right? And then to get the frictional force, you'll remember we multiply that by the normal force, right? From here. So I've put a note in here, right? That is not 0.2 newtons. That's 0.2 multiplied by the normal force n, right? So just be careful there. I've seen people mix those two things up. So we have the frictional force acting back down the slope, so that's at an angle of 30 degrees. 30 degrees, right? Our horizontal force F applied like this. So we're basically modeling the box as just like a point mass essentially. We're told that the box weighs 5 kilos, so I've worked out the weight vector, and I have my normal force, which is perpendicular to the slope. And to make the maths easy, what I've done is rotated the coordinate system by 30 degrees just so that I don't have a load of sine and cosine components when I go to equate the forces. So what I do from there is I go ahead and apply the equilibrium equations. I sum forces in x and sum forces in y in the normal manner. Just be careful with some of these components, right? So just make sure it's worthwhile going through this step on your own to make sure that you can solve that for F, okay? So that gives us our large upper bound, if you like, for our force vector F, and that's the F that if we exceed that, so if we go any greater than 43 newtons, right, then the box will slide up the hill. So that gives us our upper bound. The second scenario gives us our lower bound, right? So we make the same formulation, but in this case, the frictional force is going to be acting up the slope, right? So remember, this is the case where the box is just about to start sliding down the slope. So then the frictional force opposes that. So what that does when we go to equate the forces or resolve the forces, it gives us our lower bound on F now, because our frictional force is essentially acting, or a component of the frictional force is acting in the same direction as F. So that's how we get our lower bound for F. So that tells us that F is any less than 16.6 newtons, then the box won't be supported in this position and will start to slide down the slope. So putting both of these two answers together from the two different situations, that's where we get our range of forces F to keep that box in a stationary configuration. Okay, so that's the first example, and that's a static coefficient of friction example. Now let's have a look at a kinetic coefficient of friction example. So in this case, we've got a very similar setup to what we had before. We've got a box of 40 kilos resting on an incline of 10 degrees this time. And then we have a rope attached to the box at an angle of 20 degrees, which is pulling it up the slope. And we're given the coefficient of kinetic friction as 0.3. And the question is to calculate the tension T required on the rope to move the crate at a constant speed. So that's the giveaway that we need to use the kinetic coefficient of friction rather than the static one. So we set up our equation, our free body diagram in exactly the same way. This time I've rotated the coordinate system by 10 degrees just to make the maths a little bit easier. My weight vector always acts vertically downwards, right? And I know the box weighs 40 kilos, so that gives me a weight vector of 392 newtons. Because the box is moving up the slope, right, it's being towed by the rope, then the frictional force F opposes that. So that's why I've drawn my friction vector down here. My tension T on the rope is at essentially 30 degrees from the horizontal, because we have 10 degrees of the slope plus the 20 degrees that the rope is attached at. And then the normal vector acts perpendicular to the slope. So what happens if I resolve forces in the x and y directions, as always, is I get the following. Again, make sure that you can replicate this and you know what you're doing with these different components, right, of these force vectors, and also make sure that you can solve that system for the unknown tension T. So finally for today then, what I thought we would do is have a look at this example here from the textbook. This is example 9.29, and that's on page 441 of the textbook. And we're looking at essentially this guy on a ladder. We're told that the ladder weighs 30 pounds and that the center of mass is at the midpoint, that the person weighs 180 pounds and he's at some distance x with respect to the horizontal up the ladder. We're given a coefficient of static friction between the ladder and the floor, and also a coefficient of static friction between the ladder and the wall. So we know coefficient of friction here and also here, and they're different. And the question is to find the largest value of angle alpha such that this person can climb to the top of the ladder and the ladder doesn't slip. So, reasonably real-world example. So let's go over how to actually formulate that. So what we have here in this free body diagram is all the information that we're given in the question. So we're going to have a normal force here where the ladder touches the wall, and also a frictional force acting up the wall, right? So this is preventing the ladder from slipping down the wall this way. So that's why the frictional force acts upwards. And we're told that was mu s was 0.3, right? So our frictional force is mu s times the normal force, Na, which acts perpendicular to the wall. So the same story down here. We have a frictional force acting in this direction, which is preventing the ladder from slipping out this way. And we were told mu s there was 0.5, so our frictional force Fb, so I'm calling, basically what I'm doing here, as I forgot to draw on, I'm calling this point B, and I'm calling this point A up here. So my frictional force Fb is mu s multiplied by the normal force, which acts perpendicular to the floor at B. So the ladder is 12 feet long, and the center of mass is at the center point. It weighs 30 pounds. So I've drawn on my weight vector at the midpoint, given it some dimensions, and also I've got the guy is some way up the ladder, a distance x along the horizontal, who also weighs 180 pounds. So once I've formulated it, it just becomes a fairly routine application of the equilibrium equations to solve for alpha. So I have summed forces in the x direction, so I have the frictional force here, which is positive, and a negative normal force here. In the y direction, I have a normal force at B, a frictional force at A, and then I have these two in the opposite direction, right, the two weight vectors. So that's where this equation comes from. And then I've decided to sum moments about point B. So I've got this 30-pound force here, giving us a moment at a distance 6 sine alpha, right? So this is a clockwise moment about B, so it's going to be negative. I have this weight vector, 180 pounds, acting at a distance x, and that's also a clockwise moment about B, so that's why that's negative also. Then I have the normal force at A giving me an anti-clockwise moment about B, and that's at a distance, perpendicular distance of 12 cosine alpha. And then I've also got the frictional force at A acting at a perpendicular distance of 12 sine alpha, and that's also counterclockwise about B, right? So as it stands, because I've put this this generic or general form of where the person is standing on the ladder, I have essentially 4 unknowns in my 3 equations. I have the 2 normal forces, I have alpha, and I have x, which is the distance that the guy is standing up the ladder. So to solve for the maximum alpha that's possible without the ladder slipping when the guy is at the top of the ladder, I need to replace this distance x with this horizontal distance here, which is 12, because that's the length of the ladder, sine alpha. So if I replace that in there, I now have 3 equations and 3 unknowns, and I can solve them for the normal forces and the angle alpha. So make sure you can solve that system and you know where all of that stuff has come from, and make sure you can get the solutions that's given in the textbook. So that's it for today. A short tutorial on friction and a few examples. So keep checking for updates, keep checking for new videos, and I'll speak to you all very soon. Cheers.